Hi students, in this class we are going to deal with the Smith chart. I am trying to make you familiar with the Smith chart. Now this figure shows a complete Smith chart. Now let us see what is a Smith chart. In the previous sessions, we have seen the complex calculations of input impedance, voltage reflection coefficient, voltage standing wave ratio, etc. The solutions of the transmission line problems require complicated calculations using complex numbers. We have already done many derivations and calculations involving these complex numbers. So in 1939, P.H. Smith developed this Smith chart. P.H. Smith developed this Smith chart to analyze and design the transmission line circuits. Don't be panic seeing this figure. You may feel that it is very complicated, but it is an easy graphical tool which helps us to calculate the reflection coefficient, voltage standing wave ratio, impedance, etc. It makes our job very easy. So it is just a graphical tool to make our calculations simple. So what a Smith chart contains? First of all, let me show a horizontal axis here. Let me draw it. Here you can see a horizontal axis. And that horizontal axis is purely resistive in nature. So it is a purely resistive axis. Here the reactance component is 0. So here it is a purely resistive axis where center is marked as 1 here. You can see the center is marked as 1 here. So it represents the center of the axis or the center of the Smith chart. Now, another important thing is now above that horizontal axis, there is a semicircle. That semicircle is the positive reactance semicircle, that is J. It represents Jx0 or simply Jx. Now, it is written here inductive reactance component, that is positive reactance means it represents inductive reactance. Now below this horizontal axis there is a semicircle. Here it represents the negative reactance or minus Jx, or it represents capacitive reactance. Now a Smith chart contains two important things. The first one is the constant resistance circles. Let me draw a constant resistance circle here. Here is a circle. Here is another circle. Here is another circle. Again, we can draw many circles. These circles are known as constant resistance circles. Constant resistance circles. Constant resistance circles or R circles. These circles are having a particular resistance values. Those resistance values are marked here. Here it is written as 3. Here it is written as 3. Here it is written as 4, 5, then 10, 2, 1.8, 1.6, etc. I don't know whether it is possible for you to see the values clearly, but it is written there 1.4, 1.2, etc. So each constant resistance circle is having a particular resistance value. So these are known as the constant resistance circles. Now, in the positive reactance side, you can see a circle or a part of a circle or a curve here. Here there is a curve. Here there is another curve. Now here there is another curve. And these are known as constant reactant circles. Constant reactant circle or X circles. These X circles are also having particular values, and those X values are written here. Here you can see a value, particular value 3. It is here. It is 4. Here it is 5. So similarly, we can draw the constant reactant circle in this semicircle also. Here also you can draw that reactant circle. So two important things contained in a switch chart are constant reactant circle and constant resistance circles. Now, if we examine the values, we can see one at the center. In the resistive axis, you can see one at the center. And if you move towards the left side of that center, you can see it is 0.9, 0.8, 0.2, 0.1. Here it comes 0. The zero resistance means this end represents zero resistance means this end represents the short circuit point. Short circuit point. And here it is 10, 20, 50 or something like that, which means the resistance is high at this end, which represents an open circuit. Okay, so this end represents the open circuited line, and this end represents that short circuited line. Okay, while examining the values, we can find some particular values only. Why is it so? In this switch chart, we represent the impedances, the normalized impedances only. What is a normalized impedance? Suppose that we have a transmission line here. Here there is a transmission line having a load impedance ZL and a characteristic impedance Z0, and ZL is complex in nature, that is R plus, can be represented as R plus JX. What is a normalized impedance? That is ZNL represents that ZL by Z0. That is, when the load impedance is divided by the characteristic impedance, it is known as normalized impedance. That is R plus JX, sorry, R plus JX by Z0, or which can be written as R by Z0 plus J into X by Z0. So this value represents the normalized resistance, and this value represents the normalized reactance. So in this purely resistive axis, we represent only the normalized values only. That is, R by Z0 is represented in this horizontal axis, and also in the constant reactance circle, the values represented here is X by Z0. That is, normalized reactance is represented in the Smith chart. Now, let me show you an example. Now, suppose that we have an impedance, a load impedance Z. We have a load impedance ZL 25 plus 50J, having a characteristic impedance Z0 as 50 ohm. So we have a transmission line with the load impedance 25 plus 50J and characteristic impedance Z0. Then our normalized load impedance, that is ZNL, can be represented as ZL by Z0, that is 25 plus 50J the whole by 50, which will represent ZNL. It is given by 25 by 50 is 0.5, plus 50 by 50 is 1, so J. So here the real value is 0.5, that which represents the normalized resistance value, which is 0.5, and the normalized reactance value is 1 ohm, 0.5 ohm and 1 ohm. So how can we represent this? I'm going to show you how can we represent this normalized impedance in the Smith chart. So the resistance part, it is the real part is 0.5. So first you have to identify that 0.5 in our resistance axis. So 0.3, 0.4, here it is 0.5. So I have identified that value of 0.5 in our horizontal axis or in our resistive axis. And we can draw that constant resistance circle with a resistance 0.5. So let me draw the circle. Actually, it should be drawn with a compass. Now, let me draw this side. Okay. Now, so I have drawn that constant resistance circle having a value of 0.5. Now, what is the value of reactance? Here, reactance value is 1. So I have to, it is not -1, it is +1. So we have to take the upper semicircle. So first you have to identify the curve having a reactance value of 1. Here you can see 1. So let us draw that reactance curve or that reactance circle. I am drawing that reactance circle. Now see, at this point here, at this point, it is seen that the constant R circle and the constant reactance circle intersect. So we have to identify that point of intersection. Here the two curves intersect. That point will represent you the normalized load impedance. So I have already said three important things. A Smith chart contains, first of all, a Smith chart contains constant reactance circles, then constant resistance circles. Then the point of intersection of this constant resistance circle and constant reactance circle will represent the normalized load impedance of the transmission line. We represent only normalized impedance or resistance or reactance in the Smith chart. Now let me tell you how can we calculate the voltage standing wave ratio using the Smith chart. Now in this case, let us draw a line towards from the normalized load impedance towards the center of the Smith chart, that is to 1. So making this distance as the radius, let me draw a circle. So in actual case, we should draw this circle also using a compass. Okay. And at the point of intersection of this circle is known as VSWR circle, voltage standing wave ratio circle. So the point of intersection of this VSWR circle in the horizontal axis will give you the value of VSWR. So we have to identify that point of intersection where that circle meets that horizontal line. So it will give you the value of VSWR or voltage standing wave ratio. Now, if we know the voltage standing wave ratio, we can easily calculate the value of reflection coefficient gamma. Then another thing is here you can see the angle of reflection coefficient. If you see this, you can see the angle of reflection coefficient. From the VSWR, from the voltage standing wave ratio, we get only the modulus value of reflection coefficient. If we require the angle of reflection coefficient, that also can be found out from this Smith chart. For that, we have to extend this line. We have to extend this line. And here you can see the angle. I think it is around 82 or 83. So we can calculate the angle of reflection coefficient also from this Smith chart. And another way to calculate this voltage reflection coefficient from this Smith chart directly is, first of all, you have to measure this distance. Suppose it is dx, and then this total distance you have to measure. Suppose it is x, then the voltage reflection coefficient gamma can be written as dx by x. So by this method also we can calculate the voltage reflection coefficient. In that case also we can find the angle of reflection coefficient. And now another thing, see here it is written as wavelength towards the generator. Here you can see it is written as wavelength towards the generator. Here it is written as wavelength towards the load. What does it mean? Here in this transmission line, if we measure the distance from the load, or if we take our measurement starting from the load, or if our reference point is load, it is known as wavelength towards the generator, because you are moving towards the generator. But if our reference point is the generator itself, we will say that we are moving towards the load, because our reference point is generator and we are moving towards the load. So that is represented here, wavelength towards the generator and wavelength towards the load. Now, what are the values of that wavelength? Here the wavelength is represented as 0. Now, after completing one semicircle, so we are going along this semicircle. After completing that semicircle, here the value is represented as 0.25. What does it mean? While completing a semicircle of the Smith chart, it will cover a distance of, or it will cover a length of 0.25 lambda. 1 by 4 of lambda is covered while going through that semicircle in the Smith chart. Now, completing this semicircle also, the final values, it is 0.49. Here it will reach to 0.5 lambda. So moving along the complete Smith chart, it will cover a distance of 0.5 lambda or half lambda. So if we know the length of the transmission line in terms of wavelength, you can calculate the input impedance from this Smith chart. So it is possible for us to calculate the input impedance if we know the length of the transmission line in terms of wavelength. I'm not going into the details of the calculation of input impedance. So the important things that we have to remember is, the first one, a Smith chart is having two things. The first one is the constant resistance circles or R circles, and the second one is the constant reactance circle or X circles. The point of intersection of these two circles, that is constant X circles and constant R circles, will represent the normalized load impedance. We consider only normalized impedance or normalized resistance and reactance in Smith chart, and this is to avoid the construction of one chart for each Z0. If we consider the impedance values as such, it will be very difficult for us to draw this Smith chart because we have to change the values for each Smith chart. But if we use the normalized values, it is easy for us to use a single Smith chart for any transmission line. So using that point of normalized load impedance, we can draw the VSWR circle. From the VSWR circle, we can calculate the value of voltage standing wave ratio. From the voltage standing wave ratio, we can calculate the reflection coefficient gamma, and the angle of reflection can also be found out using the Smith chart. Now, if we know the length of the transmission line in terms of wavelength, we can also calculate the input impedance of the transmission line. That's all about Smith chart. Thank you.